Well, for this session, we have two presentations and then move on to the discussion at the end. So, yeah, let's move on to the first speaker, Robin LAMBOLL. The floor is yours.
Thank you. Yes, this talk follows on very naturally from the previous one, which ended with a comment about how you would need to include inequality aversion in order to do some of the comparisons that I was mentioning. So this is basically an attempt to do that in a way that includes several different damage functions. Before we get into this, we've heard a lot about the social cost of carbon, and different people include different things in these models. So I think we should all have a general idea about it, but you've got the ethical considerations, you've got the economic considerations, and you've got the physics considerations. So when you're considering all these things, what the social cost of carbon is essentially trying to tell you is how much effort you should put into avoiding climate change. It doesn't really tell you what that effort should go towards. I think the natural assumption is that that's the amount of money that you should then spend on some form of carbon dioxide reduction. However, in principle, it may actually be better to simply give that money to the poorest person who's going to be affected by climate change. So we're here trying to answer that question. So effectively, one way of thinking about this is comparing loss and damages to mitigation. Another way of thinking about it is, should we be advising small charities to work on climate change versus direct development action? And the question was motivated by the latter of those points. So the reason that we're comparing two cash transfers, well, firstly, they're very easy to model because you simply compare the GDP in the two cases. And in the case of charity, this is sort of like the most basic act of charity you can imagine. They also have a surprising level of overlapping co-benefits. So we know that climate change can impact biodiversity, but it is also true that cash transfers to the indigenous population around forests seems to have some protection on biodiversity as well. And in fact, in some cases, there's evidence that this might be quite a powerful way of preventing deforestation that actually has similar climate benefits to direct action. Though there is mixed results on this, for example, the red mechanism has been much criticized, which is not so different to a cash transfer. You can target it at specific things that aim at increasing health. So you'd expect, in general, people have longer lives if they're being given more money, and we do indeed see this result. But we also expect that climate change to directly cause more deaths in the world. Both of these can, in some sense, be seen as averting famine. So basically, I'm saying this is a very appropriate counterfactual for how a charity might spend money. This is not intended to be governing how governments would invest their money. So the way that we're going to make this comparison is using several different models. We need to be able to resolve the population on a very granular level to get the different subpopulations of different income levels. And the basic idea is the counterfactual is you send some money to the poorest person that exists in your model. So I'll be looking at two models, basically. One of them is going to be this from Erika et al., which is a country-level social cost of carbon. In this model, you have a modular system, so the temperature results are taken straight from CMIP 5, although I've done some updates which updates to CMIP 6. You then have the separate SSP pathways, and then there's a damage function. The damage function does not feed back to the SSP emissions. But yes, so in this case, you've got simpler modular things, and you can swap in and out damage functions. It calculates inequality over time for each individual country. So each country is optimizing, well, sorry, they're not optimizing, but they're looking at trying to do the best for their citizens, but they're indifferent to other citizens. It natively uses the growth-based damages from either the Burke paper or the Dell paper, both of which we've seen before already. And so it produces individual numbers for each of the countries to say how much those individual countries, in a self-interested sense, should spend on reducing carbon dioxide emissions. This paper received a sort of feedback article from Toll, which was basically a reformulation of the fund model, commenting that the Ricky paper ignores interannual variability. He pointed out a bug in the paper, which has been corrected. He also suggested his own rival model, which used explicit expressions for harm based on the harm of climate change to the poorest in absolute terms. This means that you can outgrow climate change, which I think a lot of economists would disagree with, but it's his assumption. It assumes also that climate change affects only GDP directly, not the rate of growth. And in addition to this, you have the convergence of different economies to a common rate of growth, which essentially guarantees that all countries will end up growing quite significantly if they are poor. There are several different damage functions used in this, but all of them are really only taken as a functional form, and then they're fitted to Toll's list of GDP damage estimates, which is a slight update of the 2014 paper, which is, to put it very mildly, controversial. The code base has a few bugs in it, which Toll has agreed are bugs, but neither before nor after fixing those bugs do I precisely replicate the findings of the paper. So I'm not going to be using this model, but we will note that it has some feedback on analysis for the RICA model. There's also the NICE model, which is a later version of the DICE damage function, which basically adds 5 income quintiles to the 12 regions. So this gives us 60 population packets, shall we say, and each region has damage dealt as a function of GDP only. And then there's relative damages to the subpopulations, which scales with the income with some damage parameter eta, so psi. So you have this relationship here. So this is a relative damage distribution, whereas Toll had an absolute damage. So you can't outgrow damage in this sense. You still affect only GDP and not growth. So regions are guaranteed to not be trapped in negative damages. However, quintiles can get trapped and can reduce in income without arbitrarily high damages. Unfortunately, the paper does not experimentally constrain zeta, so we'll constrain it to, we'll consider either the zeta equals 1 linear damages or 0, the constant damages cases. Yes, and what you find is it takes from DICE the idea that emissions reductions can reduce the GDP. We can then use that to make this follow the SSP path so as to be comparable with the above case. So we've heard a lot about utility functions. I think I want to emphasize the importance of this eta parameter here. So if you simply look at how happy people are as a function of their GDP per capita, you see for actually quite a wide variety of attempts to measure happiness, this increases linearly. And you might expect that at some point it tails off, but it doesn't really appear that any country has reached the point at which that happens yet. So this would naturally lead you to assume that you have a sort of logarithmic relationship between any happiness metric and GDP per capita. However, it's not obvious that you should care as much about getting someone from a 3 to a 4 as you do from a 5 to a 6. So if you don't, you'd want an eta value above 1, and that will lead you to have this functional form of your damage function. This is controlled by this eta, which is a relative risk aversion, which controls your inequality aversion, both over time and over space. And if you are truly altruistic, which countries may not be, but we assume a charity is, that should be the same over time and space. You've also got this pure rate of time preference, which we've seen before. Yes, so the way that you then calculate how good something is you calculate the derivative of this with respect to your emissions, and then you normalize it for the current value of $1. Now, fund and nice do this $1 to the world on average. However, in our counterfactual, we are saying you could send that dollar to the poorest person in the world. So your counterfactual in this instance, not in general, should be normalized to the value of $1 to the poorest person that exists in your model. So in the low inequality aversion limit, which to us is a special case, it's actually what most people are doing when they are doing this model because they simply didn't include inequality aversion in the first place. You can simply compare the value of SCCs with the cost of averting a ton of CO2. Usually you can find means of doing this. So you'd simply say, even in these quite conservative models, you're talking $40+. And of course, we've seen $100+ dollar social cost of carbon today. In the RICA model, you also get $100 under very similar and quite conservative assumptions. So you'd say, obviously, you should do something about climate change. You should not really worry about simply sending people money. And that makes sense because if you're not inequality averse, there's no advantage to sending people money. So you're really just saying, can you do anything at all about climate change cost effectively? And the answer is usually yes, because there are at least some means reported for averting a ton of CO2 for relatively cheap standards with neutral or positive local externalities. So in order to evaluate this more formally, we then changed the Eurikia model from CMIP5 to CMIP6 and include variability in the climate. You'll see that this doesn't really make a difference to the functional response. The other claim made by Toll of an error in this paper was also correct in the meantime. Essentially, we'll consider after this CMIP6 data, but it doesn't really make a difference to the results. So we can now consider what's the change moving from the Eurikia model social cost of carbon, which is what's reported here, to what the cost of carbon will be to an Eritrean. We're choosing an Eritrean because they are strictly the second poorest person in the SSP database. However, the poorest group is Somalians, and they are apparently living on less than $0.1 a day, which the SSP database provider has agreed is probably a mistake. So we have simply removed them from the database and proceed with the analysis. So you can see under various different assumptions, the social cost of carbon can vary over many orders of magnitude. But generally speaking, there's a linear relationship between what Eurikia would evaluate as being the social cost of carbon and the value to an Eritrean. You'll also notice from looking at this that there are a few cases where increasing the relative risk aversion from 1, so the inequality aversion from 1 to 2, results in an increase in the social cost of carbon. This is unusual because in almost all of these models in the SSP database, you assume that people get richer over time, and therefore any action that affects the future should be less favorable if you're inequality averse. However, under damage functions that affect growth, you actually can see, and in this case do see, populations in the future that are poorer than any population now. So when you actually go into seeing what this model would do, you say, for each of the various RCP pathways, for each of the various possible pure rate of time preferences and relative risk aversions, what is the amount, the social cost of carbon relative to the average Eritrean? And you see that for all of these damage functions, which are based on growth rates, the social cost of carbon is much higher than the $10 a ton CO2. So you'd strongly incentivize acting on climate change versus simply transferring funds. That is much less clear in NICE, even with 0 rate of time preference. And when you have high rates of time preference, it becomes very unlikely that you would conclude that, except possibly in very extreme cases. NICE obviously has quite a weak damage function by modern consideration, so it's possible that under a stronger GDP direct damage function, you would see a result, but it's not clear. There's a way you can invert this question and ask, how poor would someone have to be for it to be better for us to give them money versus acting on climate change? So if you say a country is undergoing a civil war, should we send them aid versus the charity works on climate change instead? Here you can answer that question. It is, of course, you're getting the same answer. The black line is the poverty level of $1.9 per day. The red line is Eritrea. And you're getting the same answers in each of the different cases, but it's possibly easier to see when you would switch over in this case. So the conclusions from this is simply that in the limit of low inequality aversion, you basically will always have an overwhelming preference for cost-effective climate action over cash transfer. However, for logarithmic utility, while climate action is preferable for cash transfers, if the climate damages are expected to significantly harm GDP growth, under relatively weak GDP damages, that is not the case. And for higher inequality aversion, you have much higher uncertainty because you simply have a wider spread of possible social cost of carbon. However, on average, in most cases, you would expect that you would want to directly transfer money to the poorest instead. So climate change may affect the poor the most. Preventing it does not necessarily outweigh their other means. It is not necessarily clear that cheap carbon credits are of net charitable benefit compared to simply transferring money. And much more work is needed to understand particularly rate of growth effects, which can result in poverty trapping, as opposed to simply looking at direct GDP damages. Thank you.
Thank you very much, Robbie. For now, there's no comments or questions in the chat box. Okay, Chao?
Yeah, hi. Thank you for the talk. I have one question. It's really about the concept of the regional social cost of carbon. So the problem is that I mean, in the poor tropic country, they may suffering more for the damage, but then they have little emissions. If you diagnose the regional social cost of carbon, probably they will also have to pay much higher price for their carbon emission. So, I mean, for that reason, I don't understand. I mean, this is also unfair estimate. So what do you think?
Yeah, so to be clear, this is why this is not what we are saying is useful for policy. This is useful for charities, yes.
Okay.
Yeah, but also that consideration stops being the case if you make this relative to their income in the way that we're suggesting in this particular model. Yeah, because basically, the reason for that result is we're saying, so that Zurichia model is just saying, if every country was selfish, what would they do? Well, countries in the tropical areas would care more. That's obviously not how we should govern the world.
Okay, thank you.
Thank you. So let's move on to the next speaker, Francesco.
Good afternoon, everyone. Thank you again. And today I'm going to present you a study that is going to look at the energy needs for adaptation and how they impact mitigation pathways. It's a study co-authored by colleagues at the EIE, Johannes Emmerling and Giacomo Marangoni, and at CMCC and Foscari University, Malcolm Mistry and Enrica De Chan. We chose to investigate this aspect because currently most of the evidence coming from IMs on the impacts of climate change adaptation on energy demand suggests that the global economy can absorb the adaptation costs related to buildings energy demand. And in a review that we conducted, we found that not all the modeling studies actually look at the long-run adjustments that refer to the extensive margins, so basically the potential impact of larger diffusion of air conditioning appliances, and even less studies actually focus on sectors which go beyond the residential sector, and sometimes the commercial sector is considered, but usually the perimeter is just related to these two, and so only to the building sector, and not also to other possible sectors impacted like the industry. And finally, usually this adaptation energy feedback is not included in the mitigation pathways, and the implications of this aspect are not evaluated in this regard. So in order to investigate this aspect, we use the WICH model, which is a model that links top-down macroeconomic structure that is hard linked to bottom-up energy sector representation. We have 17 regions, and one of the key characteristics of the model is that it has an endogenous technical change representation. So there is learning by doing and learning by researching. In the model runs that we tested, we are not including right now a damage feedback because we want just to look at the specific impact on the energy sector of the feedback that we are including, of the new feedback that we are including. And we have non-strategic setting in our case. So we have non-comparative interactions between regions. The WICH model has been slightly modified in order to implement this, what we call the adaptation-energy feedback loop. So starting clockwise from the left, we start from the regional temperature increases. And these are linked through stylized representation of reduced form representation based on empirical evidence to the occurrence of extreme temperature events. So we link the regional temperature increase to the occurrence of days, the days in a year, the number of days in a year below 12.5 degrees and above 27.5 degrees. And we implement this simulator because the empirical evidence that we gathered from past studies on the actual impact on energy demand mostly focuses on these temperature extremes. So on the center, you can see that we gathered the evidence from a past empirical study by De Chan and Su Wing, and that enables to have a representation of the impact across different fuels and across different sectors, with some the coefficients that vary across also between temperate and tropical regions. So we then fit this response in the model, and in this way we can evaluate not only the impact on actual energy demand, but how this propagates on the energy supply side, on the supply side of the energy sector and throughout the economy. Finally, we have different scenarios. The first unconstrained scenario is the reference, which is calibrated based on the indices. And then we have three alternative carbon budget scenarios that vary in terms of the stringency of the carbon budget. And this is a feedback loop because when emissions rise because of the supply side effects that need to accommodate the energy demand coming from adaptation, and when emissions rise also of course we have a feedback on the climate, and this again propagates on the regional temperature increase, creating the feedback loop. In the mitigation scenarios, we don't have the feedback on the climate because the carbon budget is fixed, but this then is investigated by looking at how the mitigation policy that is chosen cost optimally varies, and in our case, it's the global carbon tax. In terms of results, we have we can first look at the demand side impact. So we find that the additional energy required for adaptation is remarkable. So we have an electricity demand increase by 2050 of 7% with respect to total electricity global demand, and this increase in the reference scenario goes as high as 18%, so roughly 70 exajoule more. As for the mitigation scenarios, always for electricity demand, have, let's say, a halving of these additional requirements in the 2 degrees scenario, and even let's say lower impact in the well below 2 degrees scenarios. Roughly one third or 1/4 of the energy demand required in the NDC reference scenario. As for fuel demand, we have almost a net zero impact. We only have, let's say, roughly 10 exajoule of additional fuel demand in the reference. But it's important to understand that there are some differences across sectorial impact. So while for electricity demand, we find that buildings and industry, which are the sector that we include, both contribute to the demand increase. So roughly 60% of the electricity demand, additional electricity demand for climate adaptation comes from the building sector and 40% from the industrial sector. As for the fuels, we have a counterbalancing effect. So we have a decrease in building fuels demand, as it's often found by literature because of lower heating needs. But we also track an increase in fuels demand from the industry for cooling purposes. So this counterbalances, let's say, the two effects, and leads us to a roughly, let's say, negligible overall impact at the global level. At the regional level, we also have remarkable differences. So especially shocks are particularly important for the electricity demand increase in regions such as Middle East and Africa, that sees an almost 50% increase in the electricity demand in the NDC scenarios due to the increase in temperature extremes. But also OECD's demand increased by up to 23% in the reference scenario, and similar percentages found in Asia. So this electricity demand shock needs to be accommodated by an increase in the generation capacity. So we find that throughout the century, this is accommodated depending on the fuel mix that varies depending on the scenarios. And in the first 2 decades, we see that the additional capacity required is remarkably composed by fossil fuels. So we up to 85% in the reference scenario, and 40% in 2030, and 40% always in the reference scenario in 2050. Then, of course, over the time, as renewables get cheaper and the mitigation policies really kick in, we have a shift, and most of the additional electricity demand is fulfilled by either solar, wind, or storage. But what is really important is that the requirements in the first, let's say, next 2 decades, when this feedback is included, really give let's say, point to the fact that we will need an additional fossil fuel generation capacity. That gives some numbers. It's roughly equal to 200 gigawatt of coal capacity and 500 gigawatt of additional gas capacity. So as for coal, this would be roughly what is being built today, and it would be roughly 10% of the total coal capacity that we would have to add on top of the say baseline due to the adaptation feedback. So how does let's say this push towards higher energy demand really translates in terms of the implications for the energy transition? So if we look at 2 metrics represented on the axis here, which are the average yearly energy intensity improvement on the y-axis and the average yearly carbon intensity improvement rate, we can compare a situation in which a model run doesn't include this adaptation feedback loop, which are the empty scatters, with instead the model run that includes the feedback. So when the scatter shifts upward or rightward, it means that we have a higher challenge in terms of either the energy intensity or the carbon intensity, so that the improvement rate basically diminishes over on average in the course of the century. Whereas if we shift downward or left, it means that we have, let's say, an improvement and a lower challenge to the energy transition. And we see that globally and also in most of the regions, the effect that we're really capturing is mostly related to higher challenges for the energy intensity. So economies, due to this feedback, become more energy intensive, whereas we don't see a particular shift in the carbon intensity improvement, meaning that, as we have seen also in the previous slide, the additional electricity demand is mostly accommodated by a mix, which is consistent with each policy scenario. So we don't really have great challenges in terms of shifts in the decarbonization and the relative cost, let's say, of renewables investment. But we do see an increase in the cost due to the fact that the economy is more energy intensive. And another important point that we provide is an actual computation of the costs, of the energy costs related to the additional energy demand. And we do so by including not only the generation costs, so the investments in new generation capacity and also the operational maintenance cost of this capacity, but also the grid investments necessary to ensure, let's say, that the grid is stable with this electricity demand increase. And finally, also the fuel costs related to instead other uses which are not related to the electricity demand. So in this case, we see on the left, we see the annual increase in costs, in annual costs undiscounted. And we have similarly, say, proportionally to the energy demand increase, we have that the mitigation scenario halved or reduced by 3/4 the costs. And in terms of the unitary cost per megawatt hour of global energy demand, we see that this adaptation feedback would require up to $10 per megawatt hour on top of the additional take costs at the end of the century in the reference and the scenarios. Then generation costs are the one that are most relevant, especially in the mitigation scenarios, because of course substantial investments are needed, as we've seen in the previous slide. And then an important point, though, is that these additional costs somehow modify the trade-off between investing in full decarbonization in the mitigation scenario. So on the right, you see the quantification of power system cost, of total power system cost by scenarios in net present value with a 2% discount rate. And we see that in the model run without adaptation, without this feedback loop, we go from 63 trillion USD in power system costs, which are grid plus generation costs, up to 71. So we have an increase, let's say, of $8 trillion when we move from the NDC's reference to the well below 2 degrees scenario. Now, when the adaptation feedback loop is included, the total costs change, and we find that the gap between the reference and the more ambitious decarbonization scenarios shrinks, even gets negative for the 2.5 degree scenario. So we have a net benefit of investing in the decarbonization, and but this gap is substantially reduced also in the well below 2 degree scenario. So we go from 8 trillion to $3 trillion. So one of the main points of our analysis is that without accounting for the actual feedback loop, the additional cost of the decarbonization are actually overestimated. And finally, another result is the modification of the mitigation policies of carbon tax. Here we only have the three scenarios with the fixed carbon budget, and we see that globally the carbon tax will increase by up to 30% in the 2.5 degree scenario, which is the one that, of course, having, let's say, the higher emissions across the three scenarios, the highest emission across the three scenarios also entails a larger energy demand shock, and then a larger stress on the carbon policy in order to maintain the carbon budget stable. So we have a 30% increase corresponding to roughly $13 per ton of CO2 equivalent at the end of the century, while the increase in the highest emissions mitigation scenario, the well below 2 degree scenario, is relatively lower in terms of the percentage. It's just 5% increase, but that's still roughly $20 per ton of carbon additional to the value of the carbon tax at the end of the century. So even in the mitigation scenario, even if the total carbon budget is fixed, what changes is the relative is the regional allocation of emissions. So here we see only the additional emissions due to this adaptation feedback loop, and we see the increase in emissions in the reference scenario, which is allowed to increase, and we have actually an increase of cumulative emissions of 7% from the run without this feedback loop. And then instead we have a different regional, let's say, allocation of these emissions in the mitigation scenarios. So suggesting that if we run an alternative climate policies like permit allocation instead of carbon tax, then this would be affected by this feedback loop. And we also track the air pollutant emission, additional air pollutant emission related to the fact that indeed we are running and operating more coal and oil and gas fired power plants due to these requirements. So I'll briefly conclude by saying that one key point is that without really looking at this interaction between the demand side impact and the supply side impacts of adaptation, we risk to overestimate the cost of mitigation policies. And we also quantify a considerable lock-in in polluting fossil fuel generation with respect to a baseline without this feedback. And we would also go on by quantifying in damages terms, let's say, the co-benefits of mitigation in terms of air pollution, which we see are reinforced when we also include this feedback. And also we point to the fact that regional results have a bearing on climate policy design, depending, of course, on the setting we're in. And we would also point out that we leave for future work an update of the coefficients that relate energy demand to temperature shocks, and also possibly a widening of the type of adaptation measures that are taken into account by looking also at other sectors, not only industry and building sector. And finally, also go more granular in the way the energy sector responds. So there are some interesting studies done at the regional level for the US that do something similar to this paper, but go even further in quantifying, let's say, the exact lock-in, because they look at peak time generation capacity rather than at the total generation as we've done in this study. Thank you very much for the attention, and I'll be happy to take any question.
Well, I just have a question regarding the additional capacity, technological capacity, which you show for 4 scenarios, and I may misunderstand, but even in the reference scenario, the additional capacity is mainly coming from renewable energy, right? And is it
yes,
something like the power system has already become like a very low carbon system in different scenario, or
yes.
just additional capacity, it looks like this, but rest of them are relying on fossil fuel?
Yeah. So let's say that the effects in the second half of the century in terms of renewable dwarf a little bit, in the scale the effects in the first up to 2050. So the mix represented on the bottom is the mix only of the additional demand, but is actually very similar to the mix of the overall power sector. So consider that the reference scenario is already a scenario, a policy scenario. So we have an NDC and NDC policies are implemented. So we have an impact on the decarbonization, which is particularly strong from in the second half of the century. So that's why the model still invest deeply in renewables and storage in this scenario. But at the same time, these investments just occur at the later point in time and are not sufficient to keep temperatures below 3 degrees. So the actual final global increase in mean temperatures is in these scenarios 3.2 degrees Celsius. So it is a policy scenario, but so that's why we have some renewables. But looking at the first 2 decades, we really see a difference with respect to the mitigation one.
Let's move on to the general discussion. Thank you very much, Francesco. Are there any comments, or even you can ask to the session 1 speakers if you have questions. Okay, Kai.
Thanks, Shinichiro. I have a small question. I already had a small discussion with Robin in the chat. But Robin, you now included different utility functions. It also includes like regional differences. But what would be your suggestions for cost-benefit IEMs in general? Should we move away from? Should we also include these regional inequality aversion parameters or risk? I don't remember exactly which terms you use, RRA, stuff like that. So what would be your suggestions for the way forward for other models?
Yes, I think that economists would generally recommend, so I think what people like to do is to use a pure rate of time preference, and there should be a pure rate of time preference, but the pure rate of time preferences that are being used in these models are often like 3%, and that's just not the amount of interest that you can get in a risk-free loan at the bank at the moment, which, you know, that should be our main sort of anchoring point on what a good pure rate of time preference should be. And at the moment, you can't really get 1%, you know, so it's very strange that we put 3% in. But we should be less concerned with people who are going to be better off than us, and in general, we'd expect people in the future to be better off than us. So need to include both the risk aversion and the pure rate of time preference, but the pure rate of time preference can come down. So you may end up with a similar function, but it will depend on which countries are going to be.
Yeah, but the pure rate of time preference is really just for over time. So that's only inequality over time. And I think that most models do take that into account. By you can indeed take a lower pure rate of time preference. And there's been also like a paper by Drup et al. I think that's where they looked at all different values of pure rate of time preferences. But I was mostly interested in, so that's the value over time, but what about over different regions, or you even say different income groups? And that's the last one is a bit more difficult, but the first one for regions.
So philosophically, they are the same number. So you can argue this based on the idea, this like veil of ignorance approach, right? So if you don't know who you are going to be in the world, at what point in time, at what point in place, you have some risk aversion. And we can work out what your risk aversion is by how you treat different investments and what trade-off between future investment returns and like expected investment returns and like minimum investment returns you're willing to take. And if you're altruistic, you should treat everyone in the same way, and you're willing to be any person in the world. So those numbers should be all the same.
Okay, yeah. So the same over time, over regions as over time.
Yes.
But that's not what's happening now.
So in your model, that's not what's happening.
Well, it's just in RISE, in other IMs, I think. But I think so. I'm not sure.
So it is what happens in NICE. It is what happens in NICE, which is why NICE is I would say that is a more ethical model. Yes.
Yeah. Oh, great.
Thanks. I wanted to reflect on the entire session a bit, and also invite some comments on the entire session. So first, I think it was a great session because it was also very rich. We had cost-benefit applications. Those are, of course, traditional. We have seen that before, but it's moving into new spaces. The discussion the two of you just had an indication of that. The second one is this exposed analysis, where we take existing mitigation scenarios, put damages on top of it, and then compare exposed mitigation and damages, which is also very fruitful. You can do a lot of statistical explorations. Maybe we don't want to call it statistics because the scenario ensemble is not a statistical ensemble, but information on cost-benefit ratios and so on is an interesting part of that. And the third step, and I think that's the step the community as such is moving to, and that will be a challenging but also a very exciting step, is to try to integrate these into mitigation pathway analysis. That would mean it's not a pure cost-benefit analysis. It includes a target, but we would include damages, and that alters, of course, the trajectory, also the mitigation pathway trajectory. And then reflecting this in terms of costs and benefits, we get a much richer picture, as, for example, it was apparent in Francesca's presentation. So I think these three developments, the fourth one is, of course, adaptation. So bringing in adaptation is another point here. There will always be the question, once you have impacts, there's a question to adaptation. And in my opinion, whenever you do impacts, you have an implicit assumption about adaptation in that, because impact is simply the residual, what is left after adaptation. So that's a rich topic, and just my reflection on this session. Maybe there are others who would like to reflect.
Well, let me respond quickly. I think as Elmar summarized, I think impact economics have greatly occupied the session, and I think this is not by chance. I guess the new scenario process started from 2007 is actually originally planned, ended up with the integration scenario phase, where we should incorporate both impact and mitigation aspects. Therefore, I think it is now just the timing for this community to merge the both side of insights and modeling techniques into the single platform. And the other thing that I would like to mention here is actually last year we had many studies about the inequality aspects, but this year relatively less. But I think the current societal interests and also climate-related research areas would need such aspects, and therefore I'm expecting to have such kind of studies more in the next year.